What do you think is the disadvantage of bagging or advantage? Okay, let's discuss about both. What are the advantages of bagging and what are the disadvantages? Think and answer, please. What is the advantage of bagging? Obviously, since it's an ensemble technique, it will help you avoid the, it will help you increase the accuracy. And it will also help you bring in more stability. But what do you think are the disadvantages? Sorry, time consuming. Okay. And interpretation reduces. Interpretability reduces. And yes. And you know what? One other additional advantage is bagging will allow parallel processing. Because one algorithm versus another, there is no relationship. Right? Test data, that's it. But the results of the model that I built, will those be used for the second model? Results of one model is not used for another model. You have training test data. Training data keeps changing, but different algorithms are being built continuously. Algorithm 1, 2, 3, etc. Right? So since all these are different algorithms, you can run those algorithms in parallel. Right? So parallel processing is possible when it comes to bagging. Okay. All right. There is yet another disadvantage with bagging. Think through and let me know. Though we are building different algorithms, though you are splitting the data into training and test, though each time the training data set is different, do you think the training data set will be completely different? You have a data set. You're taking training data, test data. One split, done. Again, you're taking training data, test data. Another split. Again, you're taking training data, test data. Random split. There are 3 different training data sets. Do you think all these 3 training data sets will be completely different? Why will it not be different? It's all from the same data, point 1. Point 2 is, it is sampling with replacement. You're getting the data, but you're replacing the data once again, right? Sampling with replacement. Each time you take every observation, it's from the same lot. And also we discussed about a rule, out of bag rule. What is that rule? Out of bag. What does that rule say? Out of what does that rule say? There's a number. Out of the entire data, how many data points only will be repeated? Repeated. 63.2% of the observations only will be repeated. And remaining 36.8% of the data will not be repeated. So now tell me, how different do you think the training data sets will be? Very, very different, or will there be quite some overlap? There will be overlap. If there is going to be that overlap, do you think there'll be correlation between the different decision tree algorithms that are being built and the rules that decision tree generates? More or less, there'll be overlap between the different decision trees that you're building because there is overlap in the training data. There's overlap in the different training data sets. Hence, the algorithms that you're going to build, which will generate rules, decision tree generate rules, will also be overlapping. This is a disadvantage with bagging. Okay. So the base learners, BLs means base learners, will have correlation. They will be correlated. Since they will be correlated, you need to figure out a better way to handle it. Duplication also will be there. Yeah. That is also. I remove that, but even if it learns twice, that's okay. You leave it. Just leave it. Because anyways, one rule repeating again doesn't matter. It doesn't learn it again. So duplicate will be by default ignored, kind of. Okay. So one second. I've just made that flow so that I don't miss out that specific flow. Come on. Come on. Okay. So anyways, I mean, it's taking its own sweet time. All right. So to counter this, we have a technique which is called as random forest. So we are done with bagging, my dear friends. Okay. Bagging is bootstrap aggregating. Usually it is applied to tree-based algorithms. Another thing. You have tree-based algorithms, non-tree-based algorithms. Homogeneous algorithms, heterogeneous algorithms. Homogeneous means you use the same algorithm. Heterogeneous means you use different algorithms. Within homogeneous, if you're only going to use tree-based algorithms, like decision tree, only decision tree, then it's called as tree-based algorithms. But within homogeneous, you can also use non-tree-based algorithms, only KNN, for example. That is non-tree-based algorithm. Okay, let me give you a high-level indication here. So you'll have homogeneous algorithms, heterogeneous. Within homogeneous, you can have tree-based or non-tree-based. Tree-based example would be decision tree. Non-tree-based example would be KNN. Any algorithm which is not tree-based. Okay. We have generative, non-generative. Within generative, you have boosting, of course, bagging. Bagging is something which is debatable, friends. But still, based on the very logic which our friend was talking about, that fine, you're saying that different algorithms are different, but then the test data is still the same. When you build algorithm 1, you'll have train and test data, right? Going by your logic, what you told. So the test data would remain the same from the first algorithm. In the second algorithm, you're making use of the first algorithm's test data only. In the third algorithm also, you're making use of the first algorithm's test data only. So from that standpoint, it is also categorized as generative. Okay. And then you have random forest. In non-generative, what do we have? Voting and stacking. Within voting, we have hard voting and soft voting. Soft voting is averaging. Within averaging, you have simple averaging and weighted averaging techniques. Okay, at a high level, this is how it works. Okay. Okay. And then we spoke about bagging. And what is one disadvantage of bagging? The trees or the base learners will be correlated, because quite a few observations will be overlapping from one model to another. To make it uncorrelated, people came up with something called as random forest. What does this random forest do? When you have a tree and when you split it, at each split, random forest is going to randomly select only a few features. Features means what? Columns, inputs, variables, right? So it is going to select at every split, not all. So if you have x1, x2, x3, x4, x5, x6, x7, x8, x9, say you have 9 inputs and say you have 1 output. Then each time it splits, it is not going to select all 9. It will not select all 9, but it is going to randomly select only a few features, or it's going to randomly select only a few inputs. Okay, just to ensure that every tree that is run is uncorrelated. What is a forest? Forest is a collection of trees. So random forest is nothing but collection of decision trees. Forest means it has multiple trees. So forest contains multiple trees. That's it. That's it. Otherwise, it's decision tree only. Otherwise, it's decision tree only. The only thing is within random forest, you say that build multiple decision trees. If you say build 10 decision trees, then for each of these decision trees, when it's trained, at each split, only a small set of these inputs are selected. While there are different rules, the default rule is if your output variable is continuous, then at each split, P by 3, where P equal to number of inputs, would be the number of features which will be selected by default. If you have 9 by 3 is 3. Here we have 9 inputs. So 9 by 3 is 3. So at each split, how many features will be randomly selected from these 9? Now what you're doing is you're trying to ensure that you train your model on different inputs, on different observations also. When you usually split the data and train, only your observations will vary. But here your inputs are also varying. So you're training on different sets individually and then combining the results. So accuracy tend to be higher for random forest. Both ways. You're ensuring that on complete different data sets. Exactly. Absolutely. Okay. And also, this guy who has come up with this random forest also says that minimum node sample size should be equivalent to 5. Meaning at every node, if you want to split it again further, minimum how many observations do you need? 5 observations. If you have only 3 observations, don't split it because the rule is minimum 5. What is this for? For continuous, that is regression problems. Then when output is categorical, binary or multiple categories, and this problem is called as what problem? Classification problem. Square root of p is suggested. Let me use 36 inputs. It'll be easier, right? If I move on and on, say there are 36 inputs. Okay, if you have 36 inputs, p by 3 will become 36 by 3. So how many inputs will be selected? 12. Okay. Square root of p, what is square root of 36? 6. So 6 inputs will be selected. And the minimum node size suggested by this guy happens to be 1. This is the name of the person who has come up with this particular logic. No, it is used. Bootstrap sampling only is used. Bootstrap sampling. I'm trying to see if I'm missing out on anything. Just give me a minute. I made huge list of stuff that I've written, but I possibly cannot cover everything. Just give me a minute while I try to get some additional information for you guys. Okay. Okay. Now, can we do parallel processing here when it comes to random forest? Yes, parallel processing is possible because you have different decision trees that you're building. Okay, multiple decision trees, and each decision tree is a different algorithm in its own. So once again, parallel processing is possible when it comes to random forest. Similar to bagging, you can do parallel processing here as well. Okay, so bagging, first we understood about decision tree, then we understood about bagging. Now we are understanding about random forest in a structured manner. Okay. Now let us understand yet another algorithm, which is called as boosting. Let's go ahead with boosting. So bagging is bootstrap aggregating. We discussed about this. Then we spoke about random forest. within random forest, these are the various hyperparameters. Maximum number of features that should be selected at each node is determined based on square root of P for classification, where P is a number of inputs. P by 3 for regression problem, where P is number of inputs. Number of decision trees that you want to run, number of jobs you want to run, minimum number of sample leaves, so on and so forth, are your hyperparameters. Okay. Yeah, Madhuri, I like you guys asking questions because I will also probably try to answer those because I have made a list of some 112 pages. I'm not able to go to each and every section to tell you guys. So yeah, go ahead, please ask.
Sir, in random forest, you said there will be different decision trees, right?
Oh,
So
yes.
these decision trees are again built with the same rules like entropy, information gain, and the
Exactly. Yes.
root node will be different for all the decision trees.
Root node will be different. Yes, Madhuri, absolutely. You're right. Out of those, if you decide that randomly, if you have 16, not 36 inputs, you decide that randomly I need to select only 6. Out of those 6, information gain is calculated for all those 6, and from that, the one which has the highest information gain will come to the root node.
Yeah, so for categorical, if it is 36 inputs, 6 decision trees will be formed.
No.
Oh.
It is given here. Let me expand that. Yeah. For classification. Oh, yeah. Right. You're right. Sorry. Yeah, if there are 36, square root of 36 will be 6. Yeah, for classification, you'll have 6 features.
And also in normal, basic decision tree, we are forming the root node based on information gain.
Correct.
But here that we are
here
not
also information gain only. So out of 36, out of your overall data set 36,
yes.
How many should be selected here? 6 randomly. Right?
Okay. Yeah, now I
Out of these 6, which one will you use for the next split?
Which is having high information. Yes.
Exactly. The one which has the highest information.
Yes. I got it. Thank you, sir.
Okay. If you have any decimals that you get, for example, sometimes when you take square root of a number or when you divide p by 3, you need not get exact value as 9 or 3 or 6, right? You might get 6.45. Floor values are always selected. Floor means 6. 6.45 will be 6. 5.56 will be 5. So floor values are selected. Decimal part is thrown away. Okay. I think this is good enough for us. So let's proceed further. There are many things like extra trees, which is called as the random forest ensemble with extra trees and things of that kind. Yeah, same Venkatesh. Time consuming, lack of interpretability. These are the 2 disadvantages. Disadvantages are common because. All right. Now, before moving to boosting, I wish to talk about these sampling techniques. A few are missed out. Simple random sampling technique, you guys are anyways aware of. Then we have stratified sampling. Stratified sampling means you create stratas or groups. For example, if you want to conduct exit poll results, whenever you have elections, there'll be something called as exit poll results, right? And at a national level, which party will win? If you want to do that, what do? Will you go and check every person who has casted the vote? No. You obviously take a sample. Every person who has casted vote would be called as population. Not entire India's population, only people who voted. Everyone who voted would be the population of your interest. From this, when you want to do a sampling, you might say that, you know what, in Uttar Pradesh, the percentage of population is very high. So in my sample also, I'm going to have very high percentage from UP. In Goa, probably the density is less, density of people. So the number of people that you're going to choose for sampling will be less. In that way, you divide. So what are you doing? Every state might be one strata, or every district, right, could be one strata or group. From that, you are going to randomly sample and then proceed further. That's called as stratified sampling. Systematic sampling means usually used in manufacturing. You might say that every fifth circuit board, if you have a circuit manufacturing plant, you might say that every fifth circuit board which is manufactured, I'm going to take it as a sample and I'm going to analyze it, or I'm going to audit that for quality purpose. Or you might say that for the first 1 minute, I'm going to pick up the fifth one. Next 1 minute, I'm going to pick up the fourth one. Next 1 minute, I'll pick up the third. Next 1 minute, second, in that way. Because sometimes what happens is if there are errors in your machines, then maybe every fifth circuit will be defective because the machine gets reset after every 4 circuits manufactured. Maybe, you don't know. So in that way, you plan, and whatever plan you have, that's called a systematic sampling. These are probability-based sampling techniques. Then you have non-probability sampling, which is judgment-based. Judgment-based means you, based on your rationale, you decide. So completely dependent on you, on how you want to sample. And in non-probability sampling, sometimes people also do convenience-based sampling. Convenience sampling means if I say go and check with the people who are entering into the shopping mall on what phone they are actually carrying, if I give that. You might prefer a shopping mall which is very close to you. That's called as convenience sampling. But that's okay. That's non-probability sampling. It has its own share of disadvantages. However, it's fine. Okay, those are all non-probability sampling techniques. Bootstrap sampling, anyways, we discussed, right? Sampling with replacement is bootstrap sampling, friends. If you sample without replacement, it is called as jackknife method. Jackknife method means you're not going to replace. That means if I have data, say 100 observations, if I'm going to split that into training and test, if observation number 1 gets selected in training, this is gone. So for the next, you look at 2 to 100. Maybe observation 3 you randomly selected. So 3 is gone from this. Next observation would be selected excluding 1 and 3 because they are already selected. That's called as without replacement. The simple random sampling technique that we have employed is usually jackknife method only. Okay. Then we have cross-validation techniques, in which first thing is holdout method. Holdout method is very simple. The usual things that we are doing. We are splitting the data into training and test. So you're holding out to the test data. Okay. Whenever you have data, when you split that into training and test, you're building a model on which data set? Training data. So test data set is called as holdout data set. You're holding on to it. It's out of your training. You're holding to it. Bagging is a completely different technique, right? Bagging means you build multiple times you split the data in that way. This is not bagging. You just split it once, that's it. Training test. Test data is called as holdout data set. Okay, k-fold cross-validation we already discussed. If you apply stratified sampling, which we discussed, when you create stratas or groups, and then apply k-fold cross-validation, it's called as stratified k-fold cross-validation. Okay. Then we also have leave one out cross-validation. What does leave one out cross-validation? Let's understand. Leave one out. As the name itself says, we are going to leave only one out. Okay. Suppose you have a data set wherein you have 1,000 observations. You have your output variable and say you have your input variables. Leave one out cross validation. What it does is it is going to train your model on 999 observations. Only one is left out. Leave one out. So one observation, sorry, 999. One observation is left out for testing. That will be the first observation. You train one model. Then in the second model, what do? You train on another 999 observations except for 2, because second will be in test. Again, you train on 999 observations except for 3, and this third will be in test data. Again, you train your model on 999 observations except for 4, because this 4 will be in test data. So ultimately, how many times will you train? 999 times. How many times will you test? Or rather, you train it for 1,000 times and you test it for 1,000 times. Okay. But this is a stretched thing, basically. People nowadays don't use it at all because it will be hugely time-consuming task. And here there is a chance of overfitting, because same observations, multiple times you're training more than what is needed. Okay. Not accuracy. This is a way of testing only, right? The only thing that you're doing is testing. Accuracy depends on how you're using your algorithms, what hyperparameters you use. This is just on what data you're testing. This doesn't determine accuracy. Okay. All right. Now we have something called as boosting. While within boosting, we have a lot of algorithms. Today, people are using extreme gradient boosting only. They are not using any other algorithm today. Okay. And a lot of competitions, which are won because people started using extreme gradient boosting. But to understand extreme gradient boosting, we need to understand AdaBoost. Okay. And then we need to understand gradient boosting. And then we will get into extreme gradient boosting. Okay. After that, I think we'll be left with only one thing, which is called as stacking. Stacking is a heterogeneous technique, right? And this is also generative. The previous algorithms will depend, the next set of algorithms will depend on previous.